Okay. Anybody got any questions? I'm going to try to come back to get some more on that lesson we were working on. But I did want to formally cover these rules. We finished with the or, and remember you can break the or down to mutually exclusive and not mutually exclusive. When it's not mutually exclusive, of course, you got to subtract out. You have to subtract out, which is essentially what that one is right there. Let me make it a little.
I'm just having issues with how when it
That
is
independence.
when it isn't mutually exclusive, how do I find that like shared element, you know?
Well, they're going to have to tell you somewhere in there this essentially. They'd have to tell you that in some form or the other, like in that one that you were able to snatch from the jaws of defeat because I was a little bit stumped on it. I was looking for that formula, but they mentioned it in words. They said there's no mutual elements or no common elements. I can't remember exactly what they said, but they didn't state it as a formula. They just stated it in words. But if
I
you
have
got that,
I
mm-hmm.
have one that I got wrong. I still can't figure out. It was on the probability part too, so I don't know if you want to do that right
Can you
now.
share it so I don't have to go through everything?
Yeah. Yeah,
If you could share it, that would be
I just did it.
helpful. All right. See if I can copy it. Uh, All right. So, given the following information about events A, B, and C, can we, or A and C mutually exclusive, independent of both? So, it's asking about A and C. All right. So, what we need is to find out if they're mutually exclusive. Well, let's see if we can figure out the independence, because I don't see anything there that tells us about the mutually exclusive. Maybe there's something I'm missing real quick. Let's see. So,
I'm gonna post the multiple choice answers too.
okay. Once I get the solution, we can do that. So, if they're independent, then the probability of A given B or A given C in this side, which is what they're talking about, would be the same as
Sorry, that don't
C.
ignore that.
That's all right. Okay, I don't see any mutually exclusivity here because here's a little issue that I noticed. All right. Probability of A given C is not equal to probability of C. All right. Probability of A given C, though, is equal to probability of A. Okay. They're not asking about C and B. They're asking about A and C. So these two are the same. And these are the two that are not the same. All right. Let's see if I can go back.
Okay,
So
those
the
are the
choices were
yeah.
A and B are mutually exclusive. A and C are independent. All right. So there's two possibilities here for equality. So here, these are also equal. Okay. So 0.62 probability of A and probability B are equal to these two. So let's see what we can figure out about those. If the probability of A given B, and we could kind of change this to C just to, if probability of CB,
That's where I get confused whenever there's like a third one in there.
yeah, they're doing it to give you three possibles, but it's only asking about A and C, right? That's why I didn't understand the natures. I'll look at it a little bit longer. If I can't figure it out, I extended it so we can talk about it tomorrow. I'll look at it, get a little bit more time. I don't want to spend too much time if I'm not making any progress because there's something about it just me seeing here. So A and AC.
Sorry, I think I missed something. So like that last one, it's so after they post the different variables or whatever, it says are A and B mutually exclusive and are A and C independent? That's the question.
Okay, so with this right here, the probability of B given A, this right here, I think that's what they're using for the mutual exclusivity. So A and B are mutually exclusive. So A and B are mutually exclusive. Because essentially what that means, that essentially right there,
Because it
you can
equals
that it's meaning the same thing as the probability of A, B, and A, because the numerator would be the intersection, and if it's zero, then the whole thing would be zero. Okay, so A and B are mutually exclusive. All right. Let's see about the independence part. I just said, I think A and C are independent, if I remember correctly.
yeah, that's both correct.
I don't think there's anything else we can take out of there unless there's something I'm
What
missing.
makes A and C independent again?
It's B and C
No,
because
X. So the question is, are A and B mutually exclusive and are A and C independent?
okay, so A and B are mutually exclusive and B and C are independent. Is that a choice?
No. So the right choice is A and B are mutually exclusive and A and C are independent.
Well, isn't that? Oh, I have B and C are independent.
The four choices are right above my last chat.
Yeah, I saw it. It's so A and B.
might be getting ahead of myself, but
So A and B are mutually exclusive. A and C are independent. So it doesn't take that answer, the first one?
no, the correct answer is C. A and B are
A
not.
and B are not mutually
Oh,
exclusive.
wait, no, no, no. I'm sorry. It is A and B are mutually exclusive and A and C are independent. So it is A.
Yeah. So A and C are independent?
Yeah.
Oh, okay. All right. All right. 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 I thought this was okay. Yeah. A and C are independent because those are the same. See, AC is 6'2".
Oh,
So,
okay.
yeah, there we go. So A.
Okay, so that's why. Okay. Because I was looking at
Yeah,
probability
they're
and
confounding it by
probability. Yeah.
putting so many in there.
Okay.
There we go. Because
Ugh.
if the A given C is 0.62 and then the A is 0.62, so that's the sign of independence between A and C. But it looks like to me that C and B are also independent, but
So
maybe that wasn't.
in what case would they be both or neither? I don't know. I think I have a note.
Well, yeah, that's kind of a weird thing. Mutually exclusive, independent.
Because
But
there were
it's
a
just
few of
talking
them.
about A and C.
Okay.
All right.
Yeah. Okay, but no,
That's
that
why
was
that's why the question is just kind of shady to me because it's asking specifically about A and C, and then you get down there and they talk about B and all that.
right.
All right, so that should be it right there.
All right, thank you.
I'm gonna look at a little bit more of that tonight, and but that right there is that's the same thing as saying so probability B given A equals 0 is the same as saying that probability of A and B. So that's the same thing as that. So when I had did this yesterday, yeah, I was a little bit confused about that too, and I had to think about it. But yeah, because of the fact that B, so that would be equal to. So just so let's think about this a minute. If this is 0, then this is going to be 0. So that's why that right there with a check mark is the same as this. And that's kind of what I have in my notes. That the probability of B and A is 0, and that tells you about the mutual exclusivity. So that's to say that you're saying the same thing.
Okay, perfect.
Because the only way this is going to be 0 is this is 0 down here. Can't have a 0 down here because it's undefined. But if that's a 0 up there, then this whole thing would be 0, which is what they're telling you. All right. We can visualize all this stuff tomorrow. Like I said, there's a lot of stuff in there, I know. But I want to just talk about that, the just formally cover the multiplication rule, the and. All right. So, and so whenever you're dealing with and, you're multiplying. With or, it's adding. And those, like I said, fit with the definitions that we've covered with and or in the first half of the course. So notice that if two events are independent, then it's really simple. That it's you just take the probability of each one and multiply them. Okay, so that means that we say we roll a die twice, just a single one. What's the probability of getting a 6 and a 3? Well, to just show you formulaically, I've already got it down there. Make it bigger. All right. So that's going to be, so the 6 would be 1/6. There's just 1/6 on that die, and there's also 1/3. So there's your 2 probability. So you roll one die, 1/6 probability to get the 6. Roll it again to get the other 6. So that tells you that you're dealing with 1/36. All right. Find the probability of rolling a 5 on a die and then flipping a coin. Those are certainly independent because of the fact that they're two separate events. They don't share any outcomes. So rolling a 5 on a die. There's our friend 1/6 again. I might have done this yesterday, didn't I? Maybe I stopped partial way. It won't hurt us to go over again. I know we did one with that exact same values, and I just remember having done it in class too. So those are independent events. So if it's dependent, then what's going to happen is the second event's probability has to be determined in light of what happened in event A. Okay. Now, the word without replacement is usually a signal that you're have in that you don't have independence any longer. If you take a 52 card deck and have someone pull a card out and then put it back in, shuffle, and then have another pick, then in that case, those two things are independent. But if we take that card, or if the person takes that card and keeps it, and then we have our deck, which now has 51 in it, and we go and let someone pick, the probability changes. Okay. So the probability of a jack and ace. All right. Is equal to the probability of the jack times, and now formally, this looks kind of weird. It's the probability of that ace given that the jack was picked. All right. So all that means is we're going to have a little bit of counting to do for in that second pick. So the probability on the first pick is pretty easy because remember, you got 52 cards. So how many jacks are there? There's 1, 2, 3, 4. So 4 over 52. And we're going to multiply times that value. Now, there are 4 aces in the deck because there wasn't an ace picked. If we had 2 aces, then there would only be 3 now. But here's the issue is we do have one card that's outstanding that's not there because that jack that's taken out of the deck is not coming back. There are only 51 cards. All right. So 4 times 4 is 16. And then at the denominator, it's 52 times 51.
So without replacement means you just take one away from the total.
Mm-hmm. Why didn't this value look familiar? Sometimes I do strange stuff. Let's say. So these are both even. Let's see, 16 divisible by 4. Okay. Let me just see what this is divisible by. So that's divisible by 4. So that's easy enough. So 4 goes into 16 4 times. And into 2,500, 2,652, 63. And that looks familiar. I remember that 663 number. What is the probability of pulling 2 jacks on successive picks without replacement? Now, both numerator and denominator will be affected because we're keeping that card out of the deck. And in order for this to have 2 jacks, the first one's got to be a jack. And that jack's not coming back to the deck. All right. So that's going to be to formula right out. Oh, and I'm sorry, it wasn't. And then this one is just going to have that funny looking notation, but all that means is that the jack got picked and we got to account for it. So the probability of a jack is the same as it was up at the top, 4 over 52. And then I should have done something there, and I'm going to show you. It's right. It should be right, but I was going to tell you. You remember I'd said that for adding, you don't simplify to the end, but for multiplication, simplify first. So anyway, now on this one card's missing, and that one card that's missing is a jack. So there's now 4, but 3 jacks left in the deck. So if I simplify down this is 1/13. And oftentimes, if you do this, you're not going to have to simplify your final answer, at least not nearly as much. So now cross 1 times 3 is 3. 51 times 30, 13 times 51. And see, that one came out simplified. Because if we had done 4 here, we would have 12 over that big number. And then we'd have to have simplified it. So take advantage of the fact that if you multiply, always simplify your fractions. Because when you're multiplying, you're not having to worry about denominator. So, because you're not adding.
So the two successive picks, that's the two
Well,
things
when
that
you're
are
dealing with,
multiplied.
yeah, when you're
Okay.
dealing with and, I mean, it's got to be at least 2 picks. It could be 3 or more, but with you're saying both this one and this one, like the intersection and like the same thing in the set theory. And it means both.
Okay.
It's only true when both of them are true. Whereas with the or, that right there is relatable to more than one event, but you're only making one pick. You're just finding out how many different ways can I pick and have a chance. That's why or raises up your probability level and means that you got a smaller probability. Because if these separately are easier to get, the 4 over 52 or the 1/13th and the 351 are easier separately, but once you multiply them, they become even a smaller fraction. Oh, you know what? That's 12. That's still not simplified. 1 over, because they both got 3. Yeah, there we go. Make sure your fractions are simplified over there, because if you don't, they'll sometimes, half the time they'll ask you to put it in decimal, but make sure you put it to the right spot. But make sure your fractions, if you put them in, they got to be. So this was this was the final answer. All right, let's see. I think there's one more over here. In a class of 6 humans, there are 4. In a class of 10 students, there are 6 humans and 4 lifelike robots. If we pick 2 of them, what is the probability that both are robots? All right. So this is conditional, because if we've got 10 students in there and we take one out and send them to the bookstore, now there's only 9 students. So the probability of R and R robot is equal to probability of R times the probability of R given that a robot was picked on the first one. Okay. So there are 4 robots out of 10. And on the second pick, since we want 2 robots, there's only going to be 3 of them, and there will also only be 9. And as I said, these can both be simplified, so we can do that. So that's going to be 2/5 times 1/3. And now, see, there's nothing common between these two, so the multiplication will be easier and easier to simplify. So 2/15. And just always remember, pay attention to what they're asking about how they want it. Sometimes they say decimal, sometimes they say simplified fraction. I did it both here, and I rounded to 3. I think sometimes they say 4, sometimes they say 2. So watch what they're asking for, because that's part of the math, is making sure you match up, where to round off to, or whether to put it in a fractional form, because the fractional form is the exact answer. Once you round it off, you don't ever get it back. So both are important. All right. So here's the probability of a jack and. Oh, well, I'd already done that, Jack. Okay, well, that's it. All right. I'm just gonna mention this. I have not seen it except in we. I know they're going to bring this up. It's just got to be in here at some point. But you can also write the complement rule another way. If we have, and I have not seen any yet, but there may well be some in because there's one lesson after the probability one. But anyway, this is the complement rule. It's just written slightly different. So just remember, and I've got the rules. They're going to all be summed up down here. But an event occurring at least once is the same as one minus that the event does not occur. So that's one of those take to the bank kind of things. Let's and as I had said too, these are those rules that I was talking about for independence. But if you want to look at this, if you don't understand about what dependence is, independence and mutual exclusivity, I put this little thing in there. And so it gives several different examples. So that's in there. All right. All right. And so conditional probability, this is what they spend a lot of time on. So I'm going to spend the remainder of our time today talking about this and trying to do it slowly. I don't usually spend nearly as much time because they interweave it with a lot of stuff. Now, we've already looked at that formula here. This is that same one. The probability of A given B is in the numerator, it's the intersection between the two, and in the denominator, it's whatever comes last there, what follows that line, because that line means given. Now, switching them around is important. Okay, the probability of A given B and the probability of B given A are different. If you notice this, I've showed you in 2 different ways, because you can do it with probability and you can also do it by the numbers by using the numbers straight from these contingency tables. But notice that these two are different. This is the probability A given B, and this is the probability of B given A. Notice that in the case of this one, the B is in the denominator, and down here, the A is in the denominator, because that order matters there. The probability A given B and the probability B given A are different. But in the numerator, no matter which one, the intersection is the same. All right. So here's what we call a contingency table. And these things are really good for doing probability, especially conditional ones. So this is my target. And like I said, is they make a big deal out of contingency table. So I'm going to try to, and I kind of agree with it. They are good things. All right. So here's the contingency table. It's broken into 2 rows, full-time student, part-time student, and then the third row is the totals going down. And then and what this is for, it's like a log. We do this at Delgado, like students come into the tutoring lab, write down their information. So the columns are they visited 1 or few times, in other words, 1 or none, 2 to 3 times, and then 4 or more times. And then it's broken up on the rows with full-time versus part-time. All right. So we're going to be taking that chart as we do some of these problems. All right. So find the probability that a part-time student visited the lab. All right. This is not conditional, but this is going to set us up. So here's the part-time student thing. And then right here is the total part-time. So the total part-time is going to be our denominator. I'm sorry. I'm sorry. I missed not my denominator. Our numerator. Our denominator is the total. I'm always thinking ahead to the conditional stuff. And then here's the total part-time students. So if you kind of think of it like this, that everybody comes in and puts their name on a card and their full or part-time status. So there'd be 58 cards in there. 45 would be full-time students and 13 full part-time. So going in there, there's going to be fewer part-time than full-time. It looks like there was 3 times as many full-time students, even a couple more. So what's the probability? Well, it's 13 out of the total, all that visited, 58 visits, or 54 students, 58 students. And then that would be the exact answer. We can also do it with a calculator to find the decimal. I'm going to try to do both just to get you used to both. Because if you do both, then you just got to pay attention to which one they want you to enter. So let's go out to 4 decimal places. All right. Simple when you got a table. All right. So find the probability that a student visited the lab 4 or more times. Now, here's conditional probability. Let's see. I'm going to put this one up here for just a second so we can look at the table. All right. Okay. Now, find the probability that a student visited 4 or more times given, and that's a very important word. Sometimes it will be written slightly different, but that's the condition. We're saying find the probability that a student visited the lab 4 or more times if they were full time. It's like a backwards conditional statement. The conclusion coming first and the condition right there. So that means then we're following the formula. You know something? I'm just going to use this right here, that formula, and write it there so I don't have to write the formula again. All right. So our denominator as I had said, it's the condition. It's what follows the line. It's what follows the given. And in this case, all right, I was trying to clear that table. All right, so the given, so what is given is full time. So we're going to come down here, and there's the total of the full time students.
I thought it would be 45, no?
Oh, I'm sorry. Yeah, I'm looking at the wrong stuff. No, that's right. No, okay. No. Yeah, you're right.
I'm
You're right.
looking
You're
at
right.
full-time going across.
You're right. You're right. You're right. You're right. Sorry. You're right. 45. That's the total. I said it and I did something else. That's one of my tricks when I get tired here. Let's see. Now, the whole thing here is the full time. All right. And so I've circled the denominator. Now, the reason why I like the way I wrote it like this, and like I said, is you could also do that. The intersection just means where the two cross, where full time and 4 or more cross. So there's, and then here is where they cross. Denominator is whatever the total of whatever follows the given term, the condition. And the numerator is the intersection between 4 or more and full time. And then we're going to have to approximate this to a decimal. So, or I'm going to and go out to a 4 if I can. Sometimes that's shorter. So that would be rounded off. So in order to round off to that spot, I look at the one to the right. Since it's above 8, I'm sorry, above 4, then we bump the 7 up to an 8. That's a pretty standard rule. So make sure you got that part down because there's a lot of rounding.
So if it said round to the 3 decimals if necessary, it'll be 0.178.
Yeah, yeah. If this would, then it would be 0.178.
Okay.
3 decimals would be 0.178.
Okay.
With this number, that's a repeating decimal. it's always going to bump up. I mean, since it's above 7, it'll, I'm sorry, above 4, it's always going to bump up. And if it was a number like less than 5, which
Yeah.
includes 4, then all of those would just get chopped off if they're repeating. One of the famous ones is 1/3. See, that keeps repeating. So wherever you round it off to, you just chop everything else off. So if we wanted to go to 3 decimal places, everything to the right of that blue block gets chopped off.
Okay.
For the this one, which is another, what, I had one thing in mind and I did something else. This is 2/3. This is one that's very similar to that, in that wherever you round it off to, that number is going to get bumped up from 6 to 7. So the rounding off of this would be at 3 decimal places would be 0.667. All right. So I got one more down here for this, and it's just backwards. I'm going to bring it up there and so I'm going to put it here. So again, so I can say the thing. Now, this one's slightly different. Okay. Now, what I did before, and Tori, you reminded me of it, is the given now is 4 or more times. So that's what we're looking at, and then we're looking at that total. Okay, that's the total that we need right there. That's our denominator. So for this one, given they visited 4 more times, that's going to be down the denominator. And then what's the neat part? What I like about conditional probability is that numerator is all the same no matter which way you do it. And there's your numerator. Four sevenths. Oop. It'd be nice to know what 4 sevenths is. So this one would round off to all right. All right. Any questions about that? I'm running out of stuff to tell you. I got one more thing in the contingency table. I don't. I'm going to show you. We might be able to do it, in class, in the early class tomorrow, or even tomorrow, because I'm not sure that last chapter is going to take up enough space, but time. But anyway, see how it's different. That was 8 for both of them, because that's the intersection of full time and 4 or more. But here the given is 4 or more, so that's 14. Whereas on the flip flop one, given that they were full time, it was 8 over 45. And the reason why I'm bringing this up is that it's in that part 3 homework deal in the Newton. They'll have some of these things here. Okay. It's like false positive and false negative. So I like doing this because I had a kind of a fuzzy, I have a hard remembering it, and I don't like to remember things. I like to be able to understand them and then be able to put them into context. But this is the way these work. Okay. You can think of it too in the same context of like a jury trial. Okay, if a person comes in, as far as the law is concerned, they're innocent. Okay, you have the jury or you have the judge make a determination of their guilt. If that person is pronounced guilty and they're actually guilty, then that's a correct choice. But if that person was actually innocent of the crime and pronounced guilty, that's a false positive. Likewise, if you go down to somebody that was acquitted and they were actually guilty, that's a false negative. And then if they actually were found guilty, acquitted and they were actually innocent, then it's a true negative. So this is what they're talking about when they talk about those contingency tables, and they talk about that the contingency tables relate to conditional probability. And I didn't really realize that until I was studying that lesson. So it's a good lesson to know because these are quite common. And if you do take Math 203, they get a little bit more into that than we do here. This is just kind of mentioned because of the examples in the book. But all right, let's try one more of these things. I put my answers on here, but all right. So this is a nice little contingency table. It's on the rows. You got 4 different games: poker, Trivial Pursuit, Monopoly, and Wii Bowling. And then there's 3 columns for the different snacks that are possible: pizza rolls, chips and dip, and cookies. Okay. Now, you can see across here the row: 25 poker, 29 Trivial Pursuit, 38 Monopoly, 23 Wii Bowling, and then going down here, same way for each one of the snacks. All right. What is the probability of playing poker? Okay, that's pretty easy because we're going to take the total of poker over the total that are in here, total possibles. I guess this is votes or something. I'm not sure what it was. I tried to find a time for it, but
So
I didn't
something
want to
like
have to
this,
make it up myself.
you don't simplify those, right? Because of it's like
Yeah, you're going to need to simplify always.
Oh,
So
okay.
now we'll see if we can do it to both the fraction and the and then do it to a number to a decimal because you're going to have both of them. Now, both of those are obviously divisible by 5. Do you know how to tell that? They both end in 5. Okay. See that? So how many times does 5 go into? 115. It's 23. So this is 5 over 23. And now I'm going to put some squiggles here because the squiggles means that that's now an approximation because I'm going to round it to 0.2174. So if we wanted to round it to 4, what would we put there where that 3 is at? Would you keep the 3? Looks like to me, we're going to have to bump it up. Because that number next to the 3, to the right of 3 is a 9. So to round it, let me put this for 4. The second one is already rounded. This is just saying have cookies and playing Monopoly. It's still the 115 on the bottom. And then you're looking for cookies and Monopoly. So 7 over 115. The intersection between cookies and Monopoly. 7 over the total. Now, here's the conditional ones now, and these are going to have a different denominator than the 115 because the condition is going to take some of them out. What is the probability of having pizza rolls given playing Wii bowling? Given playing Wii bowling. So Wii bowling is what I want to look at first. And I'm particularly interested in right now that 23 because that's the total number of people playing Wii bowling. All right. That's our condition. So the other ones that make up the 115, we're not worried about those. So now our denominator is 23. That's what conditional probability does. It takes some of the set away. Now, where do we want to go? We want to find the pizza roll column. And here's the pizza roll column. We don't need the total, though. We need the intersection because we want the numerator. So there's our numerator. 12 over 23. So rounding it off to 4, we would just chop it right there. Because to the left of the fourth one, right to the fourth one, the 7 is 3. Approximately. Because once we chop all that off, it's no longer an exact answer. It's what's called an approximation. That's why they call it rounding. Because you're essentially ballparking it. Because if you just got a whole bunch of long numbers out there, that's good for making calculations and computers and stuff because you want to be very accurate. But the human mind can only grasp so much. And then this one, I probably should I'm doing more after this one where I turn it around. But what is the probability of playing Trivial Pursuit? Given we have chips and dip. Okay. So the given is chips and dip. And we want that total because that's the given. That's our denominator. The denominator has always got to be larger than the numerator if we're going to have a valid probability. Now, it was Trivial Pursuit. And so there's what we want. We want the intersection of the two. So 14 over 41. And so let me just keep that same thing on there, and then I'll just add one more question and change it slightly. Turn it around. Okay, so now you notice that the A and the B are swapped. In 4, it was Trivial Pursuit versus Chips and Dip. On 5, it's chips and divs given Trivial Pursuit. Okay, so we're going to use the same kind of diagram. The only thing that we're not really needing, we don't have to ignore it, but is that one right there. Now, there's our given. I should have done it with a different color. There's the denominator for our given. Okay, so then this one is 14. What? Yeah, 14 still over 29. 14 over 29. Approximately equal to, let me hit that calculator. So that's going to be an 8, because right to the right of the 7 is a 5. That means and there we go. All right, that's all I got to say today. If you want to stick around and hear more, that's fine. I'm done for the day. Y'all made me think today.
Yeah, I'm done.
Oh, thank you. We appreciate you.
The
Yeah.
back into that path thing. I think that was part 1, wasn't it? If you need some help, some more with that.
Okay.
And then in the second class, I'm gonna finish more or less the chapter, but we'll be working on it next week too.
Okay. Thank you. Have a good one.
Okay, bye bye.
Okay, thank you. See you tomorrow.
Mm-hmm. Have a nice evening.
Professor Poole, right quick. Um,
Chantel, how you doing?
I can't complain, but I noticed we're going into the lesson this week and next week for that test.
Right.
Okay.
There's probably, like I said, I'd mentioned this before. It's there's a little bit more time afterwards, but the last one has got a lot of stuff in it. So this will be a kind of it's kind of like we're coming over a hump. So we're going downhill a bit. So, the time is a little bit easier, a little bit
Okay.
easier ride than all the climbing up like we did. So,
Right. I have a very important appointment on Monday.
mhm.
I just want to let you know.
Okay, that'll be fine. I'll just tell you, yeah, one of the things I had noticed, and I was